Alright, let's do some LOL diagrams. In this first one, 1A, situation below, a spring launches a roller coaster cart from rest on a frictionless track into a vertical loop. So frictionless means no e-dis. Assume the system consists of the cart, the earth, the track, and the spring. The track being in here doesn't really make any difference because there's no friction, but we'll put it in there anyway. So that's the lowest that the cart is at, so I'm going to make that the 0 height. So when the cart is here, does it have any EK? Is it going yet? No. Does it have any EG? No, it's at the 0 height. Does it have any EE? Yes, all of it. All the energy is stored in this spring. I'm going to make it 4 bars worth, and that's up to you. When the cart is upside down here, see those little lines behind it? Those are little zoomy lines. So it's got some EK, and it's got some EG, and the spring is done, so it doesn't have any of that. So I'm going to make it 2 and 2. It's up to you. You could split it up 3 and 1 either way. And then my equation, EE on this side equals EK plus EG. That's all. That's how you write an energy equation. Repeat problem 1 for 1A for a frictionless system, no e-dis, that includes the cart, the earth, and the track, but not the spring. What difference does that make? Well, that means that if the spring is not in here, then where's the energy? Well, it must be coming in from outside. If the spring is outside the system, then it's going to come in here. And if it's not in the system, we're going to say that that is work done by the spring. And then on this side, nothing has changed. The cart is still zooming along upside down there. So now my equation looks like work done by the spring is equal to EK plus EG. And so if you see here, what's the difference between these two? This is like the energy stored in the spring. This is the work done by the spring. Those are equal to each other. It's the same thing. Just for accounting purposes, it matters whether we include it from the inside or the outside. All right. Use the same system as problem 1A, but assume there is friction between the cart and the track. Okay, so we do have friction now. It means we're going to have some e-dis. Just going to put that there right now. Why not? We got the cart, we got the earth, we got the track, and then same as 1A, so that's the spring is back in here again. So all here, I didn't write again that this is the 0 height. I should do that each time. Always pay attention to that detail. So there's my 4 blocks. Now I've got EK and EG, but I don't have as much available because I had some e-dis. So maybe I think since it's at the same point upside down, it would be at the same height. So probably it makes more sense to keep the EG the same, right? Because it's at that same height. But if there's friction, it's probably not going to be going as fast. I don't really care how you split those up, as long as you have 4 or the same total number of blocks on both sides. So here, my equation looks like EE is equal to EK plus EG plus e-dis. Right. And if you're wondering, like, when does the dissipated energy show up here? It's when the things, like if the cart in the, if the track was not in the system, then we would put it out here. All right. Here, situation is the same as 1A, except the final position is lower on the track. Okay, so they want us to, here, I want you to be consistent with this. So if it's lower on the track, that means it's going to have less EG, right? Because you have EG because you get away from the Earth. And then that means that the EK would be like this. So that's all that's different there. Everything else, cart, entire Earth, track, spring, that is all the same. And EE, that's where my 4 bars are. This is the 0 height again. And my equation. My equation looks exactly the same. It's just that if we were actually doing the math here, there wouldn't be as much EG, and there would be a little bit more of this. So not to worry about that for right now. We're just doing this all qualitatively. No numbers. For 2A, a moving car, so velocity here at position A is greater than 0. A moving car rolls up a hill until it stops. Do this problem for a system that consists of the car, the road, and the Earth. Assuming that the engine is turned off, the car is in neutral, and there's no friction. So it's why does this matter? Car is turned off and in neutral. That means it's just rolling, right? The motor's not on. And there's no friction here, so no E-dis. Now it's going, so there's some kinetic energy. This is the 0 height. That's what that y equals 0. Y is your up-down variable, right? The y-axis. So no EG. There's no springs in this problem, so there's no EE. So at the bottom, I've got only EK, because it's moving, but it's the 0 height, so no EG. And then when it gets up to here, the velocity is 0, but now it's got some height. So I think that's very similar to one of the examples I did in the notes for you. Right? Classic energy situation. Kinetic energy turns into gravitational potential, or the other way around, like the dropped ball from your notes. Number 2, repeat problem 2A, but now we do have friction. Now the road is included in the system. So put the E-dis there in the system. In other words, I'm not going to put it like coming out from up here. It really wouldn't matter for the equation in the end because you still have the one block. It's going to show up on that side of the equation. And then the rest is pretty much the same, all EK at the start, but here only 3 blocks of this because the total should be 4 because there are 4 over here. It should make sense to you, I hope, that if there was friction, it wouldn't go as high, right? Because a little bit of the energy is dissipated. And this is the 0 height again. Okay. Now we have in number 3, there's a person pushing the car with the parking brake on up a hill. Assume that the system includes the car, the road, the Earth, but does not include the person. Okay. So that means the person is going to be doing work from outside the system. With the parking brake on, what does that mean? If you've ever tried to drive your car with the emergency brake on by accident, there's a lot of friction there. So that means we definitely do have dissipated energy. Okay, so car, road, Earth, but not the person. So here, the height is 0, the velocity is 0. It's not moving yet. There's no springs in this problem. So there's nothing here, nothing here. So Where is the energy coming from? Well, it's going to be work done by this person pushing the car. Why are they lying down here? Well, I think the idea is they're like out of energy, right? They're tired, taking a nap. So I got 4 bars coming in. That is the work done by the person, WP there. And then here we have some kinetic energy. No, it's stopped there. It's not moving. Gravitational potential energy, yes. It's at a higher height. And dissipated energy, yes. You could do 3 and 1. I'm going to do 2 and 2. It does not matter. So what's my equation? This work done by person is equal to EG plus EDIS. (3b), repeat problem 3a, but put the person in the system. So if I put the person in the system, and the car, and the road, and the entire Earth, then I have to put here the work done by the person. It's going to look the same, except instead of having that arrow coming in, I'm just putting the person inside the system. Everything else is exactly the same. And you can see the equation is the same. If you put like EP, like energy of person, that's fine too. That works. All right. Number 4, A. A load of bricks rests on a tightly coiled spring. It's going to be a pretty strong spring. I'm going to launch some bricks. And then is launched into the air. Assume a system that includes the spring, the bricks, and the Earth. Do this problem without friction. Okay, so at the beginning, I'm at the 0 height, and I don't have any velocity yet, but I do have a coiled up spring. And then, in position B, it's moving. It's not at its max height yet. It's got some height that's not 0, and there was no friction. So there's no EDIS, and the spring is done, right? It did its thing, so I've got some EK and some EG. However you want to split those up, 3 and 1, 2 and 2, whatever. Equation, EE is equal to EK plus EG. All right, repeat 4A, but now with friction. Where's the friction coming from? It's air resistance. So what does that mean? It just means that we're going to have some EDIS. Everything else. And I guess actually whether it shows up here or coming out of the system, let me do it this way. You could put it there. If you did put it there, you'd have to put air inside the system. Bricks, EE. So if the air is not in the system, then we'd have 1 block worth coming out. So how do you want to split it up here? I'm going to do 1.5 and 1.5 because I think it would not be going as fast and it wouldn't get high. Whatever you want to do there. Doesn't matter to me. But 1, 1.5, 1.5, that's a total of 4, and all the energy was stored in the spring to start with. This would be like the work done by friction. So EE is equal to EK plus EG plus the work done by friction. I really am okay with either one of those. But if you do put it in here, the air should be there in the system. Repeat 4A for a system that does not include the spring. So that means that we're going to have work done by the spring. Like that. Actually, I didn't mean to put it there. That makes it look like it's in the system. I should be consistent and do it here. You notice the only difference is just what the picture looks like. The equation would be the same, but I think I want you to do it like this. So that's the work done by the spring. And the system is just the bricks and the earth now. Bricks, entire earth. They said repeat 4A, so that's with no friction. So that would look like this. And again, if you look at the equations comparing 4A and 4C, it's the same equation except we just renamed this elastic energy. Now it's the work done by the spring. It's the same for bars, just whether we locate it inside or outside the system. (5A), crate is propelled up a hill by a tightly coiled spring. Looks like those bricks. Analyze the situation for a frictionless system that includes the spring, hill, the crate, and the earth. I think the hill, including the hill, doesn't matter until there is friction. So if we have the hill in the system, that means we're going to have the E-dis in the system. Spring, hill, crate, entire earth. Okay. So what do we have here? This is the zero height, so there's none of that. The velocity is 0, none of that. So everything is once again stored up in the spring. And then when I get to here, it's still moving, so it's got some velocity and it's got some height. So how about 2 and 2? And no friction here, so no E-dis. Okay. Repeat 5A, but the system does not include the spring, and it does have friction. So that means instead of EE here, we're going to have the energy coming in, work done by the spring from outside of the system, because we put the spring outside of the system. And here, some energy was dissipated. Now here, if you want to respect the fact that it's made it to the same height, that means it would have the same amount of EG, but not as much EK. That would have to come from there. All right, so it's going to look like that. These 4 equals some of those. Number 6A, bungee jumper falls off a platform. I guess they jump, or maybe they got pushed, I don't know, and reaches the limit of stretch of the cord. Analyze this situation for a frictionless system that consists of the jumper, the earth, and the cord. Okay? So here, the zero height, they're saying here that the person does not get to the zero height, right? So they start here. Is there any energy stored up in the cord? Is the cord stretched? No. Are they at a height greater than 0? Yes. Do they have any velocity? No. So the only thing that's going on is they have a bunch of height. So they've got that gravitational potential energy. Now, down here, the height is still greater than 0. So they have a little bit of height still. Their velocity is 0, so none of that. The elastic is all stretched out, and frictionless, so no E-dis. So that must mean there's 4 here, and they still have a little bit of height, so 3 bars worth, or whatever you need to make it balance out, must be stored in the cord. Right? Doing. That cord is all tight right now. EG equals EG plus EE. Now, if you're thinking, hey, I know how to do algebra, I can subtract that from both sides. No, you can't. It's not the same EG. This is 4 bars worth, and this is 1 bar's worth. So you can't do that. These are not equal to each other, right? This is 4 worth, and this is 1 worth. So just be careful with that. Repeat 6a if the chord's not part of the system. Okay, so if the chord's not part of the system, that means that the chord is going to be taking the energy out of the system. Remember, this side is always coming out. Energy always flows through this way. So there's my 3 bars there, and everything else is going to be the same. We're just going to call this work done by the chord, and no other changes. So e.g., this equation should look exactly like this one, except we just basically changed the name of that because the chord's not in our system. That's how you do LOL diagrams. I hope that you feel okay by the end of that, like you kind of understand what's going on. You'll have more practice doing those for sure.